And I'm a flat skier. I'm not a down skier. Another minute or so for people to sign on. As I give folks just another minute, just a reminder that this is my last day talking to y'all. So after this, you guys will be leading. So with our presentations start next week. I think there are a few people who haven't signed up for a slot yet, and at this point, all of the slots are for next Tuesday. So if you have not signed up, either bribe one of your classmates to give up their later in the week spot, or you're going on Tuesday. If you are feeling uncomfortable about presenting on Zoom, I am willing to offer a few slots of one-on-one presentations with just me outside of Zoom. I really, really, really encourage you not to take this option if possible, because part of the reason we are doing these presentations is to practice presenting in front of people. So just presenting in front of me isn't as good. The other thing is then you won't be able to teach your peers, and that just makes it less fun for everyone. So if you are really feeling uncomfortable with presenting in front of people on Zoom, send me an email. We can set up a one-on-one. I would really rather not do that, but it can be an option if necessary. This semester is weird. This situation is weird. I understand. Any questions on that? Okay. Then let's get started. So today I wanted to wrap up with what I hope will be a pretty fun discussion about large scale structure of the universe. So this is kind of the last thing that we can do with galaxies in my thought, like kind of the edge between galactic science and cosmology. So this kind of gets where things get a little bit blurry, where now we're looking kind of at the structure of the universe, which we measure by looking at galaxies. So I figure we can put it in a galactic science class. But before we jump into that, I wanted to ask you all, what do we mean? What do I mean? What do astronomers mean when we say large scale structure? So how might we define large scale structure? And why was it impossible to study large scale structure before Hubble came around in 1920? So Edwin Hubble, not the space telescope, but why wasn't large scale structure even a topic before Hubble? So if you have an idea either of a definition or why we couldn't study it before then, either throw it in the chat or you can unmute yourself and let us know.
I've heard before that large scale structure is like 100 megaparsecs-ish. And then because of the like distance, like Hubble relation, we didn't know how far things away were, so we couldn't like get a picture of like the structure on that scale.
Yeah, exactly. Thanks, Erin. So yeah, large scale structure is this makeup, the kind of patterns we see in the universe on large scales. So what are the structures we see when we look at these 100 megaparsec scales? And yeah, what you said, before Hubble, we didn't really know there were other galaxies. You can't study large scale structure if you think everything is inside of the Milky Way. So until we start to realize how distant galaxies are, which we start to get an idea of in the 1920s with that Shapley-Curtis debate that we talked about way back in September. I don't know how time works. We didn't know there were other galaxies. You can't study the layout of galaxies if you don't know there are other galaxies. Perfect. So large scale structure, like we said, is essentially the structure of the universe. In cosmology, in the 170 cosmology, you talk about the universe being homogeneous and isotropic. For the most part, that's true, but when we really dig into it, we can start to see that there are some patterns. So homogeneous, the same everywhere, isotropic, the same in every direction. So galaxies do seem to be pretty evenly distributed across our sky, with there being a slightly larger number in the northern hemisphere than the southern hemisphere. I don't think we really know why. But if you start to also incorporate distances, we start to notice patterns in the amount of galaxies at different distances. And we see that in these kind of structures that we call filaments, clusters, and voids. And a lot of times this gets compared to like soap bubbles. So that's why I have this picture here where we can kind of imagine the film of the soap is where you would find galaxies, but there's these huge empty spaces in the soap bubbles where there aren't any galaxies. So these kind of, we see structures connecting in clumps where multiple bubbles meet, but these huge empty spaces between them that we call voids. And if you want to kind of see that, we can kind of see that bubble structure if you look at this distribution of galaxies with K-band magnitudes greater than 11.75 mag. So this is the 2-mass distribution of galaxies, and we can kind of see some like chain structure, maybe some bubble stuff. So this is every galaxy that we see with a K-band, so infrared, near infrared magnitude greater than 11 or less than 11.75, sorry, magnitudes. And the other thing we can see in this is that there's an area that is hard to study. Why would this area be difficult to study? What's going on in this empty space? Are there no structure there? Or is there something else? So yeah, that's the Milky Way. We can't see through the Milky Way, so there are probably structures going through here, but this is the band of the Milky Way, which we can't look through. So a lot of these maps of large scale structure, we're missing kind of these wings where we can't look through the Milky Way. So just to show this in another way, so that was 2-mass looking at infrared. This is SDSS, looking at the position of galaxies in our sky, also as a function of redshift. Again, we have, some empty spaces, both caused by the wings of the Milky Way and also just the limits of the Sloan survey, which is in the northern hemisphere. But we can start to see this kind of, again, soap bubble-like structure. Like here's, maybe that's a bubble, and this is a bubble, and this is a bubble, and they're all connected by the soap film. But each of those dots are galaxies. And we can see how these are arranged. We can get redshift of galaxies along with position on the sky to start to build up a picture of large scale structure. So how galaxies are arranged in our universe. Before we get into exactly what we see, I'm going to run through a few things that are important to consider as we do these large-scale surveys of galaxies and build up this image. So the first one is that we have to consider the differences between magnitude-limited and distance-limited surveys. Pretty much any survey is going to have one of these two limits. Most of them are going to be magnitude limited. So that's going to say, I am going to scan the sky, and because of my telescope, because of my detector, I'm going to see everything brighter than 15 magnitudes, and I'm not going to see anything fainter than that. So I have a limit where I'm not going to see anything with a magnitude greater than 15 magnitudes or something. And that means that we are seeing nearby stuff, and we are seeing bright, faint things, but we are not seeing distant, dim objects. There are a few surveys that will try to get around this by using a distance limit, where we're going to say we're pretty sure there's nothing fainter than, you know, some absolute magnitude. So I'm going to ignore all of the bright distance sources. I'm going to just not include those in my sample and focus on everything within 20 megaparsecs of the Milky Way. So I'm going to instead of, even though I'm detecting these really bright distant things, I'm not going to include them in my sample because I want to get a statistical set, a complete statistical set, and I only can do that if I look in the nearby universe. Otherwise, you introduce a problem called Malmquist bias, which is essentially, it's a lot easier to observe bright distant sources than it is to observe faint faint sources that are far away. And that's kind of what we're trying to show here. So if you have some magnitude limit or luminosity limit, this is showing stars, works the same for galaxies, where you can say, I can detect everything above a certain luminosity. That luminosity represents a different brightness, a different apparent magnitude as you get further and further away. So this line is saying we are not observing any of these sources. And as you get further, anything below, anything in this gray shaded area, we wouldn't be able to see. We're only going to see the really bright distant stuff. And this can be an issue. So like we're pretty sure that we've accounted for this, but this can be an issue when you study really distant galaxies, because there's some question of, are we observing, so like when I showed you the cosmic star formation rate history, there was that peak at a redshift of 2. So the question is, are we only observing the really bright galaxies at a redshift of 2? So we see this huge spike in star formation because we're only observing the galaxies that are forming stars. Anything that's not forming stars is going to be faint, and therefore we don't observe it. So you have to make sure you take into account this Malmquist bias when you're doing these large scale structure studies, because otherwise you might think that every very distant galaxy is really bright because you only observe the really bright distant galaxies. Now, like I said, this is something that has been taken into account. We are pretty sure that peak at a redshift of 2 is real, but we have to make sure if you are doing these large scale structure surveys that you do account for the fact that what you see really far away is going to be kind of biased towards really bright distant things. Any questions about that? And this kind of gets back to why we study the local volume. In the local volume, you can see the faint things, so you actually do get that complete statistical set of both faint objects and bright objects. And then we can use that to say, there were, 33 dwarf galaxies in the local group. So in this group that looks similar at a redshift of 1, there's probably a similar number of dwarf galaxies that we just aren't seeing because there's no way we're going to see them. So that's how you kind of start to correct for Malmquist biasing. Okay, this is the annoying Jeff. Yeah. So the next thing I wanted to briefly mention, and this is something I've kind of hand waved through before, is how we get these redshifts for these huge, large scale structure surveys. So for the most part, when we think of measuring redshifts, the way you want to do it is look for an emission line, measure where that emission line is in your galaxy, compare that to where you would expect it to be. So like with H alpha, you could look for the emission line, the bright emission line that has a smaller one that is a nitrogen 2 emission line right next to it, figure out where that is. If it's at 8,000 angstroms, we know if it was at a rest wavelength, it'd be at 6563. So you can measure the redshift by looking exactly at where this emission line is. But spectra are time consuming and observationally expensive. So photometry is a lot easier if you want to get a huge number of galaxies. And so we can use photometric redshifts instead, which are when we, there it is, okay. So when you look at how bright your galaxy is in different bands and use that to estimate what the redshift is. I couldn't find a better version of this than this, but so what we're seeing here, these dots are the color compared to Z. So all of Z is why Z never moves, because it's something minus the Z band color. And depending on what part of your galaxy's spectrum is falling in each band, you'll see a different color, so a different amount of B band magnitude, a different amount of V band, a different amount of I, a different amount of Z. And specifically this Lyman break, which we talked about when we talked about Lyman break galaxies, finding where that is can give us a pretty good indication of what the redshift is without having to find spectra. One more time. So that drop off tells us what the redshift probably is. If it happens, we would expect it to be in the UV. So as you get further redshifted, as it falls in the V band, you can estimate the redshift. As it falls in the I band, you can estimate the redshift, et cetera, et cetera. The problem with this method is it's not super precise. So you're going to be limited by how wide your bands are. But it allows us to get a lot of redshifts without having to do spectroscopy on thousands of galaxies. So positive, but slightly tricky in terms of precision. I think there's one more quick note after this one. Sorry, trying to remember. This one is a little funky, but this is something that shows up in a lot of these studies of large scale structure that I thought I should mention. And that is little h, which is the Hubble parameter. So h naught is the Hubble constant, but since the value of the Hubble constant has changed quite a bit in the past 100 years since Hubble found it, a lot of people who model this large scale structure or who observe galaxies and use the Hubble constant to find distance will instead use this value of h to try to scale all of their distances and have a dimensionless kind of fudge factor to take into account that h naught might change as we get more and more precise measurements of it. So we define h as just 100 kilometers per second per megaparsec times h equals our Hubble constant. So if your Hubble constant is 70 kilometers per second per megaparsec, then your h value is 0.7. So this is just a way that you can kind of scale distant measurements, scale angular size measurements to take into account that the Hubble constant is uncertain. And so whatever we're using is going to, whatever measurements we make are going to be affected by how the Hubble constant has changed over time. And just to kind of attempt to show this, so this is the initial Hubble plot. So Hubble's initial data found distances and recessional velocities of galaxies, and he thought the Hubble constant was 500 kilometers per second per megaparsec. Since then, we have gotten better distance measurements. So we've been able to figure out that h naught should be closer to 700. And so the shift here and how that changes the position of these points, shifts these points to much further distances. So just being able to, instead of having an x-axis that is distance, having an x-axis that's distance times little h will allow you to have units that make sense. So you're still working in units of megaparsec. But now the fact that you are using some calculated value of h naught in all of your models will be taken into account, and it's easier to kind of rescale and reshift as we get more precise measurements of the Hubble constant. So when you see little h in a paper, that's what it means. It's really just kind of, yeah, this dimensionless fudge factor that allows us to take into account the fact that we don't know the Hubble constant with great precision. Any questions so far? here, I think this is my last one before we get to talk about some of the fun things we see in large scale structure. But this one's really important for considering how we actually measure large scale structure. So the 2-point correlation function, or XI of R, so this little XI, is a measurement of how clustered galaxies are. So the big idea is how likely are you to find another galaxy within a certain distance r of your first galaxy? So if we know there is a galaxy at position A, if we go 10 megaparsecs away, how likely is it there is a galaxy within that volume, 10 megaparsecs surrounding galaxy A? And this tells us a lot about the structure of the universe because it says something about just like how clustered are galaxies, how big are superclusters, how random is the distribution of galaxies in our universe. So a Xi of 0 would be totally random. So this is 1 plus Xi, so totally random would be this value at 1. Higher Xi means you're more likely to find a galaxy within that volume or a couple of galaxies within that volume. So as you get closer together, you see higher Xi values, meaning it's just more likely that you could find another galaxy within that volume, that co-moving radius. So co-moving radius is another, it's essentially distance, but it's distance independent of Hubble parameters. So it has to do with this is kind of more of a cosmology thing than I'm totally comfortable with, but it's essentially like if you have a scale length that's not going to change as the universe expands. So I think it's kind of going into that. But the thing to see, yeah, like I said, as we get closer together, you're more likely to find a galaxy than if you look really far away. And so that tells us that galaxies are clustered at certain scales. If you get too close, then you won't find another galaxy, but I think this graph isn't essentially showing that. So eventually you're too close and it's unlikely you will find another galaxy. But for the most part, what we see is that galaxies do seem to be spatially correlated with each other. So galaxies tend to clump together in clusters. We don't typically find one galaxy just off by itself. And so this is important, yeah, when we want to try to understand just the distribution of galaxies and how likely it is that galaxies are going to clump together. So another thing that we notice when we measure large scale structure is that we can see there's some differences between how galaxies clump when we look at different types of galaxies, different galaxy classifications, so different, whether you're looking at spirals or ellipticals, and then also if you look at different luminosities of galaxies, how bright your galaxy is, that's going to have different spatial correlation functions. So that's what this is attempting to show. This W of P has to do with that Xi value. Just how likely is it that we're going to cluster? And what we see is the brighter galaxies, so galaxies with lower magnitudes, are more likely to be close to other galaxies. Fainter galaxies, you're just slightly less likely to be close to another galaxy. So this is a good sign for hierarchical structure formation, so saying that we grow galaxies by taking small galaxies and merging them together, because that we would then expect for big galaxies to be near a lot of other galaxies, allowing them to build bigger over time. And just to show that in another way, this is again that Sloan data where we have position on the sky and redshift, and then they're color coded based on the color of the galaxy. So redder galaxies we can see are more clumped together. Bluer galaxies tend to be less clumped together. So this is what I've said again before, but just kind of showing it in this large scale structure way. Giant ellipticals tend to be in the center of superclusters, whereas spirals, blue spirals, tend to be more on the outskirts of clusters or along filaments, which might lend credence to the idea that spiral galaxies maintain spiral structure and maintain star formation by not going through a lot of harassment from other galaxies, by not colliding and merging and becoming ellipticals. But we can get an idea of that galaxy history, galaxy evolution type of stuff by looking at large scale structure, and large scale structure as a function of either galaxy type, galaxy color, galaxy mass, or galaxy brightness. So now, with all that in mind, we can talk a little bit more about what we have found and just what the definition of these different things are. So when we do make these maps of galaxy position in the sky and redshift, we see that galaxies are grouped together, as I have said, in structures that we call clusters and superclusters. So these clusters can have 10 to 1,000 or so galaxies. We split them into rich clusters or clusters with 30 to 300 galaxies, and poor clusters or groups, which are 10 to 30 or so galaxies. So that's the Milky Way is in one of those groups. We're not really in a cluster because we only have 38, so maybe we're on the edge, but tend to call it the local group, not the local cluster. Rich clusters have galaxies move around slightly slower, so they move in their cluster with radial velocities of 100 to 500 kilometers per second, just because there's more big galaxies pulling on them and slowing them down from different directions. Poor clusters have slightly higher radial velocities within their galaxy groups. Clusters will then group together to form superclusters. So we get clusters of clusters, pretty much it's like fractal kind of things as you look at these, where we just see different things splitting off. But so we have clusters of clusters. So this is just showing kind of the local volume. I think this is a non-astronomer image, so they have a scale of 100 million light years instead of parsecs. But what we can see is we're not quite in the Virgo cluster, but we're on the edge of it. We're moving towards the Centaurus supercluster over here. There's a Shapley supercluster. All of these have different names of either astronomers or different, or the constellation they appear in. So we've measured a bunch of different clusters and we've given them names, and we can come up with this little map of where we are and how that relates to other superclusters. There's a really big one down here. I don't know. Sorry. Clusters, besides having galaxies, clusters are also where we find that intercluster gas or intergalactic medium. So that's where the IgM is. And we can measure that by either looking for those jellyfish galaxies or by slightly seeing it a little bit by looking in the X-ray emission. So it will emit slightly in the X-ray, and we do seem to find quite a bit of hydrogen gas in between galaxies in these clusters. The supercluster we are in, kind of shown again, is the Laniakea supercluster. So it's a cluster of about 300 to 500 galaxies that include the Milky Way and the local group. And because some of these images were made using the Keck telescopes on Mauna Kea, it was given a Hawaiian name. So Laniakea means open skies or immense heavens in native Hawaiian. And I'm pretty sure I'm pronouncing it right. I listened to a YouTube clip right before this class, so hopefully it's still in my brain correctly. And as I talked a little bit about when we looked at the local groups, if we measure the motions of galaxies in the Laniakea supercluster, we see that they all seem to be moving towards this great attractor that's over towards the Centaurus supercluster. So all of the galaxies within this supercluster have similar motion, making them part of this one bigger Laniakea supercluster. In between galaxy clusters, there are those empty spaces called voids. So these are kind of the bubble part of our soap bubble. If the galaxies are the film, the actual soap, this is the empty space between that. So these are very, very large areas with little to no galaxies. They can be over 100 megaparsecs across. So again, very, very big, much bigger than galaxies themselves. And understanding the size and the number of voids is really important to understanding the composition of the universe. Because if we want to think about like the density of the universe, if you're trying to show that we have the critical density to be flat, you need to take into account the fact that there's a bunch of empty space in the universe as well. So the average density of the universe is going to be pretty affected by the fact that there are all these empty voids. So if you want to make your model of the universe and show that we are in a universe with dark energy, so lambda, and cold dark matter, you need to make sure that that can recreate all of these void structures we see. So yeah, if you see this, I think I've said this a couple times, but if you're reading a paper and it says, we're working with a lambda CDM model, that means that we are working with lambda, which is dark energy, and then cold dark matter. And it's the most popular model for the universe that we have at this point. Every once in a while, there are some faint blue galaxies in voids, so they are not completely empty, but they seem fairly empty for the most part. And like maybe those faint blue galaxies are ones that somehow got kinematically kicked out of a group or something, and have therefore managed to stay blue over time because they've just been slowly using the gas they have and creating new stars over time without any interactions with other galaxies. Yeah, question.
So in the voids, is it just defined as not having galaxies, or do they also like not have IgM?
So we're fairly sure that they don't have much IgM either. So most of the gas seems to be following the position of galaxies. So we think voids are pretty dang empty, but there might be some pretty diffuse gas that is just hard to measure. So like where the exact line is, the boundary is, I'm not sure. How close to densities of 0 these voids are, I am not 100% sure off the top of my head. Any other questions? It's a good one though. Yeah. Okay. So between structures and kind of making up the rest of the soap bubbles are filaments. So these are the largest structures we see in the galaxy, and they're these chains of galaxy superclusters. So that's kind of what we're trying to show here. This is a model of the universe now. We're kind of shifting from observations. Everything so far has been observations. We're going to shift into thinking about models now. But we can see these kind of like tracks and paths where we get clusters kind of joining together along these things that look kind of like when they show the brain and they show where all the neurons are, and it looks really similar and it's all trippy. Anyways, sorry. But the filaments, the main thing is that, again, understanding the distribution of filaments also is really important if you want to prove that we are in a lambda cold dark matter universe. So the number of filaments we would expect, the sizes and structures of filaments tell us quite a bit about what the universe is actually made of. One other little thing to throw out before I completely transfer into looking at models is something that we've noticed around our own So again, we are kind of in here. Horologium, that's what it was. Sorry, I can't pronounce that either. But we do see this something that's even bigger potentially than a filament that's called the Sloan Great Wall, and is what we see here. And so it's this kind of big collection of superclusters spanning a redshift of 0.4 to 0.12, which is pretty wide when we think about redshift. Again, like those small redshifts cover large distances. Small, saying it bad. So like going from redshift of 0 to 1 is 7 billion light years. Going from redshift of 1 to 2 is 3 billion light years. So these like shifts in really small redshift are going to be pretty large scale shifts, even though it's not a huge difference. But since we're looking at low redshift, it is a big difference in actual space. Does that make sense? Sorry. This is the non-linear redshift stuff, which is kind of weird to think about. But the big point is that this is kind of the largest structure we have seen in our universe. And it shows that there might be more to large scale structure than just voids, clusters, and filaments. Maybe there are these other bigger things that are called walls, and just understanding how many of these there are, how common they are, tells us more about how clusters cluster. So how do superclusters clump together, as well as just how do galaxies and groups clump together. So let me start with this. Okay, so now we're going to start transitioning to thinking about how we make these models and what we can then learn from models of the universe. So what I'm showing here is the illustrious simulation of our universe with time moving forward. And this is just a computer model of what the universe should look like over time. And by comparing these computer models to observations, we can test different theories about what the universe is made out of. Whether or not, if you kind of shift your physics, if you need to shift your physics at all to get the structures we see. So if we tell a computer this is how physics works, do we actually see galaxies arranged the way we do in the universe? So these are great for understanding both getting really pretty videos of universal evolution, but also for testing models of what the universe is made out of, how much dark energy there is, how much dark matter there is, how we can possibly get galaxies forming and changing over time. This is a long video, so I'm going to pause it there. But you can look at the rest of this, and also we will play with this simulation, so no worries. I think Rain is going to tell us more about the illustrious simulation, so I'm just going to kind of step through quickly what goes into it. But the main idea is any model of the universe needs to start. So the earliest models start with just dark matter and gravity. So if I take n dark matter particles and tell them how gravity works, what happens? So if we just run time forward, I have some number of gravity dark matter halos, and they should pull each other together through the forces of gravity. If we get close enough together, they should potentially crash together. How likely is it once they crash together, are they going to stick? So that's like the stickiness. How likely is it that your dark matter going to pass through, or is your dark matter going to hit and stick? And we really just, this first step, we're really just worried about the law of gravity. So F sub g is gmm over r squared. So we need to know how far away is every particle away from every other particle, and how massive is each particle in your simulation. And then you just run time forward and see what happens. And you do get some clustering just with that, but that's not quite enough to actually see what's going on in the universe, because our universe is not just dark matter. There's also a lot of other things going on. I don't 100% understand how they involve dark energy, so I'm not going to focus on that. But I'm sure they do. I just don't understand it. So after you have your dark matter, we then add baryons as well. So Baryons are more complicated. They don't interact only through gravity. They also interact through pressure and like weak and strong nuclear forces, electromagnetic forces. So now we need to add other physics into our models as well as soon as we introduce baryons. So when we throw gas into our model, gas particles can interact through gravity. So gas particles can pull themselves together, but gas particles can also have pressure and push themselves apart if they are hot enough. So you can get heating and cooling in the gas. And if you want your model to reproduce what we see in the universe, you need to take this into account. Once you have gas in your simulation, you also need to add the fact that that gas can collapse and form a star. So if you have enough gas clumping together, that can turn into a star. And this is where we start introducing this idea of feedback. So stars can have stellar winds, stars can explode in supernova, or just nova on the surfaces of white dwarfs. And all of that will push material out and will lower the density, will make it less likely for new stars to form because we're clearing the gas out of a galaxy through these stellar winds or supernova explosions. Now, you can also have positive feedback from stars. So as you form more stars, some of them do go supernova, that clears material out, but that also dumps material back in other parts of your disk of your galaxy. So that will speed the formation of new stars. So stars can both be a source of negative and positive feedback. For either more new stars is a negative feedback, we slow down star formation, but also more new stars means potentially more new stars somewhere else as well, after those new stars die and explode. And then the final step is to add a supermassive black hole to every dark matter halo. So you have to say, in my simulation, if I have a dark matter halo of above a certain mass, then there needs to be a central supermassive black hole in that dark matter halo. That central supermassive black hole is mostly going to attract things through gravity. So again, just laws of gravity. How are things going to get pulled towards that supermassive black hole? And how will that heat the gas through accretion onto an AGN? And then again, how will that be a source of either positive or negative feedback? So AGNs can have jets which spew material out into intergalactic space. So that will slow down star formation, but they could also be a source of new gas into another galaxy or to a different part of the disk. Or as you're moving gas towards it, that might spark star formation in other parts of the galaxy's disk. So main idea is we start with dark matter and gravity, we add baryons and some amount of feedback, both positive and negative feedback from forming stars and black holes, and that allows us to make pretty dang fancy models of the universe. So that and very, very, very powerful supercomputers. So just to show another one, this is the fire simulation, or latte. I can't remember if it's fire or latte. I think it started fire and then they moved to latte at some point. But this is showing, instead of the large scale structure, just one big galaxy slowly accreting gas and stars over time. So kind of focusing on this guy here. We can see it pull in some smaller galaxies, merge together. Changing color is going to tell us something about what kind of stars are going on. So those colors do correspond to things, which is cool. And we can also see a little bit as the galaxies merge, every once in a while there's kind of a puff out. So that might be a sign that they're modeling some negative feedback as well. So we've got gravity pulling things together, and we've got negative feedback pushing things out. Maybe an AGN turns on where we get these kind of bursts of stuff flying out again and again. As we get closer to a redshift of 1, we do see or a redshift of 0. There is a bit of spiral structure that seems to form. You can kind of see spiral arms, just showing how incredible some of these models are. So this is instead of a model of the entire universe, thinking more on a small scale of a couple galaxies. But both of these types of models tell us a lot about how galaxies change and evolve. So This is a galaxy that never went through a major merger as to this time, and it seems to have formed a nice spiral structure, despite the fact it was accreting a lot of smaller things and went through some pretty violent moments where it was outputting a lot of gas. Models that include dark matter and gravity, as well as gas, baryons, and feedback, do a pretty great job of recreating what we see in terms of galaxies in the universe. And before I let you out to play with Illustris and think about these simulations and large-scale structure and what we can learn, I wanted to really quickly, because there won't be a lot of time in the next few weeks, just point out that my Whitman account email will eventually go away. If you want to get in touch with me to talk about galaxy research, to talk about grad school, to talk about Wyoming, to just ask me questions about, ask me for pictures of Levi, I don't know. This is my Gmail, wherever it is, and that should not go away anytime soon. So this is just an option. I'll add this slideshow to our list of slides. I wanted to make sure I said it today because starting next week when we do those presentations, we're gonna have to move through them fast. So it's just a bit of a warning for that. I think I have made 7 slots and I said the presentations were 10 minutes. So that's 70 minutes. We have an 80-minute class. This is gonna be close. There are a lot of you, which is awesome, but it means that we're going to have to kind of cycle through these presentations fast, and you probably won't be hearing from me much in the next week and a half. But please do feel free to reach out to me if you do have any other questions about anything and think I could be helpful. I have had a blast working with you all despite the world, and I hope that I have been helpful in some ways. So I wanted to say that now before we got to our activity. Any questions for me right now before we start things? Okay. So assignment for today is the exploring large scale structure assignment. I think this one is fun. I spent too long playing around with this, so I hope it is a bit of a fun way to maybe de-stress looking at pretty things for a little bit before getting into this kind of finals crunch period. But there's a quiz that's going to walk you through some guided questions about the Illustris Explorer. So the Illustris Explorer is this, oops, I think I zoomed out too much, seeing replications. So the Illustris, it allows you to explore the Illustris model of the universe. And this is probably our kind of highest bandwidth thing that we will look at. So do give it some time to try to load. And also if yours is loading well and you want to work together, you're in breakout, when I put you in breakout rooms, your lower bandwidth classmates might thank you, because this one, there's a lot of stuff going on here and it does take a bit of time to actually figure itself out. I also give you some suggestions for what you can have this actually show you. So you can look at different properties that Illustris models and try to answer some of these things, questions that I give you. So just a few questions where we can kind of run around and think about what we need to make these simulations of large scale structure and how they help us learn about the universe and galaxies and all that kind of stuff. So I'm going to open breakout rooms, and this is what we are going to do for the last 30 minutes. So once you're done, and this is what we're turning in for our last kind of participation point thing. My Zoom is giving me slight issues, but I will do my best to bounce between breakout rooms, so hopefully I will be able to do that. If anyone has questions as I get these set up. Okay, not hearing anything, so I'm going to go ahead and open rooms. And again, we have rest of class to work on this. Feel free to sign off as you finish.